we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connection with country, and we recognize their valuable contribution to Australian and the global society. Today, it's my great pleasure to welcome Martin Lynch. Martin doesn't need introduction in these circles, but just a brief one. Martin is currently pursuing a PhD degree at the Sustainable Minerals Institute on the topic substitutes for copper, and he's supervised by the director of the institute, Rick Valenta. And so this presentation doubles up as a review for his PhD as well. He's currently retired. He worked 15 years in his own business, in his own renewable energy business, and 25 years in various roles in the mining industry. Martin is an author of one book entitled Mining in World History. Today, his talk is going to be about substitutes for copper. Please join me to welcome Martin.
Okay. Is that better? Yeah. Okay. Now, I've been approaching this PhD essentially by looking at the end uses of copper, of which in a sort of a broad sense, there's about a dozen of them. And just taking each of those dozen and looking at what the substitute for it is, and secondly, what the history of substitution is, what the difficulties are, and so on. And then I aggregate all of that to sort of get a picture of the substitutability of copper. And so I'm going to start by sort of, you'll have noticed that I've said replacing copper with aluminium. And the reason for that is that aluminium is actually the main substitute for copper. So what's on this slide is the top 8 end uses. So they go down to the 5% of total copper consumption is where I sort of cut it off. And those top 8, you know, account for about 2/3 of copper usage, or did in 2023 anyway. And as you can see down the primary substitute, that 6 of them, or 7 of them rather, are have their primary substitute as aluminium. One of them, valves, stainless steel. There's a couple of important uses which don't have aluminium as their main substitute. Probably the most significant other one is telecommunications cables, which has optic fiber. But pretty much all of them, if aluminium's not the primary substitute, it's one of those substitutes, which is why I say aluminium and not substitutes more generally. Now, substitution has a long history. It's often sort of overlooked, but there is in fact a long history of substitutes of copper. And it's never really been a comfortable process. It's always, basically it needs a driver. Now, very often, historically, that driver has been shortage of copper. Not always. Sometimes it's been the invention of a better technology, optic fiber being one example. But drivers kind of, the main driver that I have seen is shortage. Now, shortage is correlated to pricing. And so it sometimes looks like, well, pricing drives substitution. But in my opinion, that's not the case. If pricing stayed completely flat and you had shortages, you would still get substitution. So it's not the price driving it. price sort of picks out the end use which is to be substituted, but you would still get substitution without any pricing change. So what I want to do firstly is just take you through a bit of the history of shortages of copper. Now, I could talk for hours about this graph because there's just a fair bit of study that I've done into it in the past, but just to sort of say this, that there's nothing new about shortages of copper. Between the first, if you're looking at the graph, now the graph is of the LME copper price in real terms. So you can see that between 1950 and the mid-70s, it was trending upwards. Then the price trended downwards between the mid-70s and the early 2000s, and then sort of steeply back up again in the early years of the China boom. Now, what's driving the first period of shortage is essentially the post-war boom, as it was called. So that's when the economies of what you might call the advanced nations shifted from being pretty much in a city, not particularly well equipped with, housing and so on. But the economy is spread from the inner city to the suburbs, and you've got this huge expansion of material wealth, so actual goods. So people's houses became bigger, they owned 2 cars, they got new fridges, all of this being sort of pent-up demand from the Depression and the Second World War, the deprivations of those. So you had a big boom between the 1950s and the mid-70s, and the copper industry really couldn't keep up, but nothing could keep up. So all the prices went up in that time. But then you get to the mid-70s and all of a sudden you get a shift. Everyone's got enough cars and their houses are big enough. So the demand growth slows down, and copper demand is now growing at sort of 1% a year. And that's between the mid-70s and the early 2000s. But copper demand's only growing slow, but copper expansion capacity is actually growing pretty fast. Particularly in the 1990s when all the Chilean mines came on stream. So you got a big drop in pricing. And finally, China comes along and it does its industrialization and urbanization. And all of a sudden, pricing goes right back up because the copper industry just can't keep up. So that's sort of, I just want to sort of give you that background because I'm going to come back and refer to it in a bit. Now, there is a current shortage, and I won't go into why I think that because it'll take too long, but be that as it may, there is forecasts of greater shortages. Now, there's 2 sort of reasons for that. The first one being that the energy transition, being reliant on electrification, is going to need a lot more copper wire and copper everything else. So it will drive demand higher than it currently is. Or the growth in demand will become more rapid. But more importantly, I actually think more importantly than that, the ability of the supply side to respond in terms of new mining capacity is becoming poorer. It's harder and harder to bring on new mines. They're more expensive and they take a lot longer to actually bring from discovery to production. So you've got those 2 sort of twin influences which are going to create shortages more than they currently are, at least, in the 2030s and 40s. Now, don't take my word for it. That's pretty much the unanimous view of 8 different forecasts, which, and there are probably more of those that I've managed to find that have been done since 2020. So, options for addressing the shortage. You can increase mine production, but that's already been assessed by these various forecasters, and they're saying, well, yeah, that's not so easy to do. I mean, there's a lot of suggestions about how you could do it, but doing it means reversing a 20-year trend of declining production growth. Look, there's heaps of potential in recycle. Last year, just take last year, 60% of the copper that came out of commission was thrown away, 60% of it. And that doesn't include the hundreds of millions of tons which is in landfill already. So the recycling of copper is actually pretty poor. But that said, the sort of scope for improvement in production or supply rather is not that great with recycling, because copper stays in use for about 30 years. And you've got to go back 30 years ago. It's 40%. So we're recovering 40% of the stuff that was put into use 30 years ago. So it's really not that much, unless the landfills start being mined for copper, which it could happen. And I don't see why it doesn't happen. I don't understand it well enough to know the dynamics, but it's certainly a fruitful area for study, in my opinion. So the third one is, well, what about accelerating the shift to substitutes? Now, I'm going to focus on that from this point. And 7 of the 8 forecasters previously referred to say, well, that's not going to happen. And essentially, the forecasting groups, at least in those 8 of them, take quite a dim view of substitution. They basically say, look, it's really never been that important, and it's not going to be that important going forward, because if you could do the substitution, it would already have been done. That's the assumption, right? Now, I might be sort of misquoting them, and there might be a lot more subtlety to that, but that's essentially the conclusion. But I'm here to say, I guess, that forecasters don't always get that right, and I don't think they are right. So the reason I say that is that substitution's been a big deal right through since the 50s. In that first period of shortage, leaving aside building wire, which it's at the top, but it's one of the minor ones, there was a lot of substitution going on. Probably the most important one was the shift of utility power cables from copper to aluminium. There was already a lot of aluminium being used in utility cables prior to the 50s, but it really shifted in the 50s and 60s. But not only that, transformer windings, which were copper, and everyone said, well, there's no way you can go from copper to aluminium. Well, they did go from copper to aluminium. And there was a whole lot of other things. Industrial machinery used to have a lot of copper parts. They went to different parts using alloys and all that sort of thing. So there was a lot of substitution. Perhaps surprisingly, even in the period of surplus, there was a lot of substitution. There was a couple of reverse substitutions. The building wire, which I'll talk about later on, so I won't dwell on it here. Even utility power cables, which are quite price sensitive, they went back to copper. But what didn't go to copper was what shifted away from copper was telecommunications cables. They went from copper to optic fiber. And the reason for that was just the explosion in communications. And copper wire just couldn't handle the volume. Whereas optic fiber is, for the same thickness of optic fiber, you can transmit about 1,000 times more information, and it's a lot cheaper too. So it was, by the time it became a well-proven technology, it was an absolute no-brainer to go from copper to optic fiber. Also, in the automobile sector, there was a lot of substitution, and the driver for that was the higher fuel prices. So you wanted lighter cars, and to do that, you took copper out and put aluminium in. One of the bigger things there was changing the heat exchangers in the car from copper to aluminium, and I'll talk a bit about that later as well. Finally, in this most current period of shortage, you can see how the price shifts up quite dramatically. And this is one of the reasons I say that pricing is really not the driver of substitution, because with a price shift that big and with an aluminium price staying exactly the same, if price was a driver of substitution, you would have seen a lot more substitution than actually did happen. What did happen, though, it was mostly invisible. I think most people, even in the industry, might not even have noticed it. That the aluminium, the utility power cables went back from copper to aluminium, and plumbing piping, and the small business that I had was was partly involved, well, a big part of it was in plumbing, so I saw this myself. Plumbing piping went from copper to plastic, and that was a big shift. And you would not find anyone going back to copper now. You know, you get some traditionalists who prefer copper, but pretty much everyone will use plastic. And the only reason they didn't do it was, and this is a thing that I think is a theme throughout substitution, is that it's just hard to make the shift. Once you make the shift, it's fine. Now, my estimate is that substitutes have, in the total demand that's been, or the total demand growth since sort of the 60s or the 1950s, substitutes have supplied about 30 as a minimum and up to 40 and perhaps even more. I won't be too bullish about that. A lot of that depends on how much how much importance you place on telecommunications cables. But between 30 and 40% of the copper that was demanded was actually supplied by substitutes. So it's been a very important influence on managing the global copper market. Now, I'm going to move on a bit because I don't want to run out of time here. That said, you know, even after all of that substitution, there's a hell of a lot of scope remaining. And this table will give you my opinion of it, right? So again, taking those same 8 end uses, this time looking at my assessment of their substitutability. Now, the ones which are colored in sort of pink, they have substitutability, which is pretty much total. And now I say the definition of what substitutability, as I define it at least, is at the bottom there. And essentially it's saying that there really is no strong negative impact of going to the substitute, either in terms of product quality or product reliability or the cost of. It's a different way of doing it. So there's a different mix of cost, but overall, you're not really losing anything as a consumer if you go from copper to the substitute in these ones of near 100% substitutability. More difficult in some of the others. Electronics, you pretty much can't go from, you can, but you get a much reduced quality, right? Vehicle harnesses, the problem with vehicle harnesses is that the thinner the aluminium wire gets and the more likely it is to break. So and in vehicle harnesses, that's the sort of wiring in a vehicle. You get these tiny little wires and you really can't substitute those. Or you can, but again, the risk of breakage is higher and all the rest of it. So you get a loss of reliability. In motor windings, and this, Rick will tell you that this is sort of my favorite subject. And the reason is it's such a complicated technical area. Yeah. That I've just really been sort of I probably misunderstood it completely, but I've been getting into it. And my assessment is that there are some types of motors that you can use aluminium windings in, and they're the motors that, let's just say your garage door, where you're only using it, 20 minutes a week, you know, so the risk of breakage, which happens due to vibration, is much reduced. Whereas if you're using a motor on a factory floor and it's running 95% of the time, very high risk. So there's different risks here. So there are some motors you can replace the copper with aluminium, but many that you can't. But overall, in my opinion, minimum 50% up to 60%, you could substitute without any loss. So you might be thinking, well, then why don't you do it? I mean, it's copper is a lot cheaper. It's a lot more plentiful, and it's not going to run out. Sorry, aluminium's not going to run out. It's a lot cheaper. So why don't you use it? And that's a good question, right? So, and this is sort of what the rest of this discussion will address. What are the barriers to substitution? Now, off the cuff, and you know, if you meet someone, a very superficial answer is, well, copper's got better electrical conductivity and it's got better thermal conductivity. I mean, what do you want? But in reality, they're not big deals. All you need to combat the lower electrical conductivity is a thicker wire. That's all you need, and it happens to be a lot lighter as well. You know, so it depends on what you're measuring. You just have a slightly bigger wire, and in most applications, that's not a big deal. Thermal conductivity, well, probably most of you here know more about heat exchange than I do, but really the material of the wall is the last thing that's important in heat transfer. It's getting it from the wall to the fluid that's the problem, and that you're using fins and all that sort of thing. But the thickness of the actual wall is not the issue. So yeah, sure, copper's a better conductor of heat, but it doesn't really matter in the whole scheme of things, is what I'm saying. So those two issues are not why people refrain from doing substitution. The reason people do refrain from using substitution are these things. First of all, aluminium, if you've got an aluminium wire and you sort of cut off the end of it, off the end of the insulation to put it into a termination point, it will immediately form an oxide layer straight away. And that oxide layer doesn't conduct electricity. So there's that issue. Now, you can overcome that by designing the termination to break through the oxide layer, and that's what people do, right? So it's not a insurmountable problem, but that's one reason why people don't use it. The oxide layer also prevents soldering. Now, soldering is a very quick way to do a connection, and when you can't do soldering, you got to do something else, which is more expensive, takes more time, and all the rest of it. So the oxide layer is a problem, and that's why people say, I'd rather use copper, because copper doesn't have those problems. The second reason is that aluminium has a lower tensile strength. So if you've got a wire and you hang a weight off it, it'll break more easily than copper does with the same thickness of wire. But once you compensate for the greater the greater thickness of the wire, then it sort of wins back some of that strength, but it's still lower. Probably more importantly than that, the fatigue resistance, and that is the ability to not break when it's vibrating. So that's worse than copper, and kind of always will be. You can combat it with alloys, but it's still hard to do. So that's another reason people don't use it, particularly in motor windings, where the motor's vibrating. And thirdly, and this is most important in heat exchange, certain types of corrosion, aluminium's more vulnerable to. But then, on the other hand, copper's more vulnerable to other kinds of corrosion. So it's not just one way, but there are certain applications, particularly in heat exchange, where aluminium is sort of shied away from because of that corrosion. But really, as I've sort of explained there, you can overcome these things without, there are some costs involved, but not that much. So then what's really the problem here, you know? And so I'm going to take two examples. One of them is building wire, and the other one is the room air conditioners and the heat exchangers inside them, and just tell you a bit about what's really stopping this. So now, if you wanted to alleviate a global shortage of copper, the quickest thing you can do is go from copper building wire to aluminium. It surprises me that it hasn't already been done. There are reasons for it, but it's such a low-hanging fruit. It still surprises me. Aluminium has widespread regulatory approval. So you can use it, you know, because I say that because that's an argument that people say, oh, it's not approved. Well, it is approved, actually. It's much cheaper than copper wire, and it's much lighter. Now, the lightness of it is sort of lessened by the fact that it's all got to be insulated, and the insulation is, because you've got a bigger wire, it's somewhat bigger, but still it's much lighter. So if you're pulling it through a building, it's a lot easier to do. So there's a lot of advantages, but why does no one use it? Well, these are the reasons. First of all, there is, if you go online, if you say, can I use aluminium in buildings? Half the articles you read will say, no, it's banned. Well, it's just not banned, but that's the urban myth. And if a builder said, look, I'm going to sell you a house, it's got aluminium wire in it, 2/3 of the customers will say, well, I'm not buying that, it's a fire hazard. You know, so it isn't a fire hazard, but that's what people think, right? Now, I'm not having a go at those people because it's all over the place. It's a widely held urban myth. I don't know if anyone here actually thinks that, by the way, but I think as a builder, you'd be kind of morally obliged to say, oh, I'm using aluminium wire here. And at that point, someone would Google it and come up, fire hazard, right? So they won't buy it. So that's a big reason why people don't use it. In fact, building wire is mostly used, or aluminium building wire is mostly used in commercial buildings when it's used. And the reason for that is that the people involved in that are kind of probably more technically minded than the house buyer, right? The second thing is that, look, aluminium does have to be installed in a different way. And the reason is that oxide layer. If you put it into a standard copper termination point, because aluminium expands and contracts more than copper does, what you'll have is that, particularly when it expands, or contracts rather, you'll have some of that initial conducting area, it will be exposed to oxygen. It'll be exposed to the air, and it will immediately form an oxide layer, and the conducting area will become less. And then the next year it'll do it again and become less and less. Eventually it'll become a hotspot and it will cause a fire. So you've got to put it into a different set of terminations is the point here. They're not difficult to do. I mean, those terminations have been around for a long time, but they do have some technical differences, which you just have to take account of. The last thing is that all of those different terminations, try and find them. Try and find aluminium wire. Like just in the course of doing this, I've rung around a lot of places. And as I said, I used to have a trades business. Not that I'm any expert in it, it's just that I know a lot of electricians, and none of them use aluminium wire. None of them know how to get it. That they were all trained in it when they were doing their apprenticeships, but it just isn't around. So that's why people don't do it. And the last thing, and this is probably the most important part of it, is that if you were to do that, if you were to say, look, I'm going to wire up this house with aluminium, you'd save about $800, right? And in the course of someone coming along and buying a $450,000 house, and you tell them, well, it's got a fire hazard built into it, they're not going to buy it, right? So for $800, you lose a sale. And that's why people don't do it. It's not because you can't do it. It's because there's all these little barriers which stop you doing them. Now, I'm just one more example. Room air conditioning heat exchanger, right? So there's two kinds, essentially. The one on the left is copper tube, aluminium fin. And they've been around for a long time. Back in the 50s, they all used to be copper tube and copper fin. But in that first period of substitution, the aluminium fin came in. So what you get there, and I've been to factories where they do this, you basically loosely put the aluminium fins on it, and then you put this bullet through the tube, and it expands it and it tightens it all up, and you got a nice heat exchanger. It's actually really easy to make. Now, the other one is all aluminium microchannel. And essentially, that's a different thing. It's all aluminium. So you got these very thin tubes, very thin. That's why they're called microchannel. And you weld it all together. Now, we've already talked about how aluminium doesn't solder too well. It doesn't weld too well either, because you get that wrong and you burn right through the aluminium. So it's a more difficult process, but it's a more efficient process. Microchannel heat exchangers use a lot less refrigerant, and they use a lot less energy to achieve the same cooling or heating. In fact, they were first created for aircraft in World War II because they were lighter. And they're a lot lighter, which is important. Now, just to look at the share of the market. Motor vehicles, by the year 2000, that share of the market was in place. So microchannels, 95% of the market in motor vehicles back in 2000. And just the enthusiasts, really, the people who like the tradition, had the other ones. Now, the building aircon figures are today, right? Today, you've got microchannels are kind of specialty. Again, just from my background, I knew a lot of people in the aircon game, and I just visited them all one day and said, look, what do you know about this? No one had even heard of aluminium microchannels in Australia. They didn't even heard of it, right? Let alone use it. So now Australia is a bit beholden to the Chinese manufacturers. They're more common, microchannels are more common in the USA and certain other markets, but their market share is pretty low. The 10% is an estimate. I think it's increasing as times change, but it wouldn't be 20%. So the question becomes, well, why do people not use all aluminium when it's way more efficient? It really doesn't cost that much. It's more difficult. It's more costly to build the factory, but it's less costly to run it. So there's a different mix of costs. But there's, it's not a big cost difference overall. Well, the first thing, and this is, to my mind, quite understandable, is that microchannels, that they do require a completely different factory. And as I said, the fin and tube heat exchangers are so easy to make that when someone's thinking, well, I need more capacity, what am I going to do? They kind of think, well, it's just so much easier to do this fin and tube one. It's easy. So now that's not to. There are plenty of people or occasions when you'll take on the harder task because you need to, but you don't need to. The market is still very strong for the fin and tube heat exchangers, and that's where the default is. But there's another reason, and this, I'm told by people familiar with the market, is particularly true in the China market, and that is that there have been some quite bad experiences with making the microchannel heat exchangers and not properly corrosion protecting them. So you make these heat exchangers, you put them out in the market for 5 years, and then they're all coming back because they're corroded. And the memories of those sorts of disasters stay with people a long time, and so there's a risk aversion involved here as well. There's a real issue. To properly corrosion protect them does cost a bit, but it's not sort of a game-changing cost. It's more the risk aversion that's important. And finally, there's basically the lack of a reason. Like the reason the cars went to the all aluminium is that they needed lighter. They needed lighter radiators and heat exchangers, and smaller. Because the microchannels are much more efficient, the heat exchanger can be a lot smaller, and it is. So they're the reasons. Whereas with the building aircon, it doesn't matter how big they are or how heavy they are, because they're never going to be that big or that heavy, and so it just doesn't matter. So I guess where I'm going with all this is that the reasons people don't move to substitutes is not some big technical reason. It's just, there's just not a good reason. And when you do it, there's not a big payoff. So there's just better things for people to do. And that's why they don't do it. That's the reason. So I'm going to finish then by just summarizing it and say that there really is plenty of room for substitution of a sort of a no regrets substitution of copper. But the reason people don't do it is that there just aren't big payoffs for doing it. And they've got better things to do to earn more money. You know, that's the reason. But that's when copper is available. When copper is not available, that's when you get substitution. That's when the wheels start to turn of substitution. Because if you can't get it, you need to use something else. And when you need to use something else, you know, as I've sort of described here, there are well-established alternatives that people know about, and just consciously reject. And so when they need to do it, they can do it. And it's not even a risk. Once you do it, you think, oh, that wasn't so hard. And that seems to be the history. That there's not too many cases of substitution happening and then reversion going on. And that's why I say that any future copper shortages really are not going to be shortages, because what will happen is that people, as you can't get copper, will use other stuff, because that's the way it's always been. And I will finish it there. Thank you.
Thank you, Martin. And there's more room for questioning. So.
Good morning. My name's Andrew. I work in comms here at SMI. So my question is, if this does successfully transition, do we have, like the substitutes, do we have enough bauxite, and will the same thing happen to the aluminium price once there is more demand for aluminium?
Yeah. Now, I can't answer that other than what I think, right? Because as part of this PhD, I am going to study that issue, right? My first impressions are that there's plenty of bauxite, and it's a lot easier to bring on because they're surface deposits. So my opinion is that no, there's not going to be the same issue. Copper's getting deeper and deeper. Bauxite isn't. It's more of a quality issue with bauxite than it is a quantity issue. So now I think if you were to go to bauxite, you wouldn't have the same problem.
So do you think thanks for that, that was fascinating, and things that I don't normally think about in my daily life. But the question perhaps is, you talked about people's reticence to actually change. So do you think that, what are your feelings for the life cycle analysis of the copper world versus the aluminium world, and whether or not that might actually be a way in which people would be keen on using aluminium in place?
Now, I'm going to answer it this way, right? And that I hesitate to use the word ignorance because it's sort of a bit pejorative, but I think there's just a lot of lack of knowledge about substitutes. In the industries, like I don't, one of the sort of shortcomings at the moment, as I see it, is that I don't have that much conversation with people in industry. But when I do, I get the feeling that the whole substitution issue is definitely understood, but it's sort of boiled down to a series of kind of one-liners. That's a problem. You know, there's not a lot of inquiry, really. It's not an open question a lot of the time. So I think there's a fair bit of lack of knowledge around the subject. Certainly there's not a lot of inquiry around the subject. And in the academic world, the papers I've read, I don't think it's dealt with very well. So the life cycle analysis that I see that could be beneficial is just that, right? Just sort of exposing the issues. I think if a little, I guess the way I see it is that shining a bit of a light on the whole issue and putting it into quantifying it and all the rest of it could do a lot for this. Does that answer your question? Sort of, yeah.
Thanks, Martin, for the very good presentation. I liked it. So one question that I had was, when you show the substitution, it seems that actually there are certain spaces in the copper that it's much easier to substitute them. Do you have any data in terms of showing the projection of the growth in demand in different areas that copper is used, and how that substitution might address some of them? Because like if, for instance, if there is an electronic copper that used in the electronic devices is growing very fast and we cannot substitute aluminum there, then the substitution in area that the growth is not as much might not be able to cover it. But if we can actually have some of those data, well, I'm not sure if you have that or not, to show if the substitution really can help with the growth in copper demand as well. Because if it's in certain area that it's not really aluminum can be replaced, then it might not help us as well.
Yeah, I do have good data because some of the forecasters give you a pretty good idea of where the sectors into which the copper's going. But you got, the way I look at it at least is to, and I'll just give you some examples. Let's just say all of the copper growth was going to go into electric vehicles and renewable energy cabling, right? Just take that assumption. You really can't use copper in electric vehicle motor windings. Because the aluminium, because the aluminium wire is thicker, it means the motor has to be bigger, it loses efficiency. It's just not really going to happen. So you're not going to use that. But if someone said, well, now we've got to use all our copper in electric vehicle motors, you would just go somewhere else, which was easy to do. So it doesn't, to my mind, doesn't really matter where the growth is. Going back, I mean, it does to an extent, but there's plenty of the other uses which are waiting to be substituted and can easily be, well, you know, relatively easily be substituted. That's to me the issue.
That's a very point. I think I agree with that. But the key point is, like, if the growth, for instance, in electric vehicles are much higher, so then, but the growth in, for instance, buildings or something like that is not as much. So my key question is, I mean, it doesn't mean that we shouldn't go that way, but to me, it's more about having a good projection, also the shortfall, because even if you substitute all of that area, because the growth in that space is not as large, it might not be contributing too much to filling the gap. But having that understanding, I think, is very good, because at least we know how much this process can fill the gap and how much it still exists. Yeah.
Well, let's just take buildings. You could have the same building activity for 10 years, but you're still using copper each time, right? So there's no growth, there's zero growth, but you could replace all of it. That's why I say the breakdown of the growth is not so important. It's more the breakdown of the whole thing, right?
Thanks. So I think there are about 8 online questions. Okay. Probably I'm going to handpick and then come back later. So there are similar questions from Stephen Mickelworth and Craig Brown concerning the clean energy state of aluminium production. So from Craig, he says aluminium production is electricity intensive. Australia effectively exports coal in the form of shiny ingots. This is now threatened at Tomago. Will aluminium production be able to compete for clean energy? In that similar vein, so Steve is also asking a similar question. He says it takes roughly 50% more emissions to produce aluminium relative to copper equivalent. In addition, the surface footprint of aluminium bauxite mines is greater than copper mining. On the other hand, copper mining associated with long-lasting and risky mining impact of tailings. in short, he's saying, have you looked at the environmental implications of swapping aluminium with copper?
Yeah, well, similar to the previous question, I'm going to look more closely, right? But the answer I'd give you as it currently stands is that because aluminium is very electricity intensive, for the same source of electricity, it will have emissions of about 3 times that of copper. But because aluminium's half the weight per sort of length of wire, it has about 50% of the emissions, which is what the questioner said, right? So it's got half the emissions, or 50% more emissions. That can be balanced against, there are more other non-emissions environmental impacts associated with copper. Now, the reason I say that is not because I know that myself. It's just that there are some quite good studies. Eleanor Leb pointed me in this direction. There's some quite good studies written on what are the implications of making heat exchangers from aluminium versus copper. And they've gone into it in quite detail. And it's not just one, there's 3 of them, and all different teams. And all of them have concluded that, yeah, there's more emissions, but in terms of the other side effects or the other impacts on the environment, when you add it all up, it's about the same. That's their judgment, not mine. I can't really speak about it in detail, but that's where it is.
And on that note, actually, that's a great segue. I was going to ask about, have you considered some of the exposure standards? So for instance, in Australia, next month, the aluminium welding fume standard is going from 5 milligrams per cubic meter to 1 milligram per cubic meter. And next year, with the move from the exposure standards to the exposure limits, the copper fume limit's going down to 0.2 milligrams per cubic meter. Have you considered in any of this how people's ability to actually work with some of these materials and the new limits will factor into any of this?
Actually, to tell you the truth, no. That's kind of news to me. In fact, I might catch up with you later and you can tell me where you got that from.
Okay.
I'd just be kind of interested. Yeah.
Do we have any more here, or do we go online? Okay. You please pass it to Gordon.
Thanks, Martin. Interesting talk. I guess 2 questions. The first one, should we be buying shares in aluminium? And I guess the second one, given that there's this, let's say impasse about making the jump, do you see this as a wait for the market to sort itself out, or should governments be doing things actively to promote this change, do you think?
Yeah, the shares thing, I don't know. You might be better off buying copper, but I think it's a good question what you just raised. The reason is that when someone's thinking I've got to build a copper mine, they're not thinking, well, I could build a bauxite mine, and for another couple of $1 million, I could make this aluminium processing facility, which doesn't exist. The difference in expenditure between the mining side and the processing side is huge, and it's the processing side that's actually the problem, right? It's getting the products made, and it does seem to lack an end-to-end oversight, which is where government, not control, but some sort of body that's not just individual companies might be useful. That's all I would say. Regulation, no, as long as I would say that regulation, the danger as I see it is that the International Copper Association is an excellent lobby group, really good, very effective. And you might say, well, we need to support copper mining, and that's the last thing you need to do. So it's more a matter, perhaps it's more a matter of keeping the government out of it in that sense, but trying to get a greater oversight of the end-to-end process.
Okay, we'll take more online questions.
Sure.
So from Dev Ramachandran, he's asking, so building on geopolitics, what caused the price to stagnate during the period of shortage, but oversupply caused the price to drop? Did geopolitics play any role in price movement? And
This is in the surplus period?
yeah,
It was oversupply. It was capacity. You've got the demand for copper, global demand, growing at 1% a year. That's pretty slow. I mean, historically, that's very slow. You'd have to go back to the Great Depression to get that sort of growth. And you know, miners are pretty optimistic people, in my opinion. And you know, they've got this new deposit. They're going to bring it on. And the forecasting too is terrible. So you know, it's just not. I think you would be hard pressed to find a time since the 1950s where shortages have not been forecast. You know, it's always going to be a shortage, and because people always overlook, in my opinion, substitution. So no, there was no intervention. That was just a market thing.
one from Andy Reynolds. So he says the bad repetition in North American residential comes from mixed copper aluminum terminations with different expansion properties, leading to poor connections and arc faults. An example of installers poisoning the well, which also happens with heat pumps. So in this case, which market forecasters, even they are giving substitution a fair hearing due to such bad repetitions in North America from mixing copper and aluminum and terminations?
Okay, so that's what the problem is, right? So if you have an aluminium wire and you connect it to a brass or copper fitting, then you've got different thermal expansions, right? And that's what causes the hot spot. What you need to do is have aluminium wire and aluminium termination, because they've got the same expansion, but that you can also, because, and but you often don't take the risk of expansion by putting it into a lug and then crushing it so that it becomes that they called it sort of cold welding. You know, it's not welding, but it's basically crushing the wire and the fitting together so hard that it can't move at all. So yes, if you're using aluminium wire and copper fittings, traditional fittings, you're sort of asking for trouble. And that's the thing you've got to change.
Last one from Esther Maha. So if I'm not mistaken, the last sentence from the second slide from the last mentioned that people don't switch to substitution because it is expensive to build new facilities. If substitution is better overall, would you think that the idea will pick up or accelerate with the rise of mandatory PRI and substantial financing? Are we going to see a change if there's mandatory PR or some financing programs in place?
What's PRI?
I don't know. Sorry.
Okay.
That person could ask it.
Yeah.
Give him permission to ask the question.
I'll just get to that slide. Is it the second last one?
So the last sentence from the second slide from the last. Sorry. Second slide from the last.
Is it that one? I don't know.
Should think so.
When you say the second slide, like the...
So when you come back.
Right, okay. I'll go back to that. This one? Okay. There you go. The second, now which, sorry, I'm getting this wrong, right? The last sentence. Yeah, right. Yeah, look, it's not a, it's a solid investment. This is what, there's quite a few of these factories now being built, right? So it's not like it's and by companies that really you'd think know what they're doing. So they're clearly commercial ventures, right? It's just that I don't think that they are far better. So what these people have got to do, what these companies have got to do is build a new factory that's completely different to their traditional mode of manufacture, quite different. Now, it's well-established technology, so I'm sure they feel pretty comfortable. I'm sure they've kind of got the right people and the rest of it, but you've got to retrain everyone. You've got different, risks in the manufacturing process. And at the end of all of that, it's really not a better investment than if you'd stayed with the fin and tube.
All right, please join me again to thank Martin.
Thank you.
Next week we have Paul Greenhill from AMC Consultants, who will be talking to us about using machine learning tools and multivariate analysis for metallurgical sample selection and predictive geometallurgy. So please join us next week.